Welcome to this video on inductors. This is part 4 of the videos covering inductors. We're going to continue to look at how the inductors behave in the circuits, and here we have a parallel configuration so we can test our understanding and challenge ourselves to see if we actually understand what's going on. So I'm using a FET simulation again, and I have a link below in the description. These are great ways to test to see if you understand what's going on. So I have a battery, a resistor, and these resistors have equal resistance values, and I have an inductor at the top. And why I have two different variations of the same thing here is because I want to take a look at what happens immediately when this first switch down here is closed, and then also what happens when it's been connected for a very long time. So all the rules that we came up with from before should be the same. And so what we're going to say is that initially the inductor will behave as though it's not even there. And the reason for that is because it's resisting the change. So as soon as the current starts to increase, it resists. And so we're going to say that for that first split second, L, the inductor, is going to act, or it acts as a break in the circuit. In this case over here, when it's been connected for a very long time, the inductor is really just a wire, and it's going to behave as such. And so what we're going to say here is that L acts as a wire, as if it's not even there. So what's really important about this is that resistance, or the resistivity of the wires, is effectively zero. And so that's what we're doing. We're talking about that as the value. Now you can get this approximation pretty well because the resistance of these resistors can be so much more than the wires that it doesn't really make a difference. So let's go ahead here to our simulator and see what happens. Well, the prediction's probably going to be that nothing, so let's label these two junctions here, A and B. We'll say that there's going to be no current through this top branch, obviously, because there's a break in the circuit. And in this case over here, from A to B, we'll have current that is equal to just the EMF over R for the initial position, and then this would be EMF over 1 over R plus 1 over R to the negative first. And let's see if that's exactly what does happen. Okay, so we got a pretty steady current here right away. The total, of course, is increasing as this increases, and this is increasing up to, it looks like, the same value here because I have the same resistance in both. And we can see that the rate of change is dropping, so it's not increasing by as much as it was initially. And here we go, we have it set at what we predicted. So if we were going to graph this resistor as a function of time, this ammeter as a function of time, what we see happen is that it goes to its steady state, and the steady state over here is going to be equal to the potential difference over the resistance. Okay, so we have something that looks essentially like EMF over R because they're independently connected. The current through this middle branch here had stayed constant the whole time. It didn't change at all. So if we were going to graph the I versus T for this middle set over here, we'd see that it pretty much just stayed the same value the entire time. And this over here, the total current for the circuit, okay, was going to look very similar to this top branch because of that. But of course, we're going to have less resistance, less total resistance than any individual one resistor. So this asymptote over here is going to be the EMF divided by, and this is 1 over R plus 1 over R, and that's of course to the negative first. So you can see that the resistance at an individual resistor is larger than the equivalent resistance of both added together, and that's just from our old original circuit values. So that's pretty interesting. Now if I did not have a resistor up here, it'd be pretty bad, because what would be happening then is that this would be basically a short circuit, and it would just be pulling more and more and more current until it started a fire. Let's take a look at now what happens if I cut the current in this main part of the circuit, or in this total area here where the power supply is. Let's talk about what should happen first. So I'm going to pause the simulator and let's discuss what should happen. If I open this, I've got no more current in this branch down here at the bottom. Now, because I have had an inductor over here, I have some sort of energy component because I have this magnetic field. There's no more change in the current in this branch, but as soon as I cut this over here, the current is going to start to drop. And because it's going to try to prevent a drop in the current, it's going to push in the opposite or in the same direction. And so it's going to act as almost like a little battery for a split second, and then will slowly die out. So let's see what happens there. So I'm going to cut the current, and we see that there's this drop. And it's not immediate, and the drop becomes, the rate of change gets less and less and less as it goes to zero. And it actually makes sense, because what's essentially happening when I first cut this branch down here is that the inductor is trying to prevent the drop in the current, so it's going to push in the same direction as what the current was right before it was cut, and then will eventually go towards zero. So that's something we want to think about. This scenario that I have up here on the screen on the right at this time has to do with when you first connect the battery. But when you first disconnect the battery, you have to think about the fact that the opposite would happen. So the main rule of thumb here is to think that the inductor is always going to oppose a change. So if the change is when you first connect versus the change when you first disconnect, it's still going to be opposing change. It's just going to be either opposing a decrease or opposing an increase. In the next video, we're going to take a look at what if we put a capacitor with an inductor, what should happen.